All right, today we're going to go over the examples from Chapter 5, Section 1. And in this chapter, we are focused on perpendicular bisectors, angle bisectors, and the relationships that those things form. So in our first example, we are asked to find the measure of segment BC. So what I'm going to do first is highlight what I'm looking for. I'm looking for this segment right here, BC. And I see that the other information that I have is a measurement for this segment here, which is 7.2. So what I know, and I'm not necessarily doing a proof, but what I'm trying to do is to prepare myself for a proof later and try to make connections with these things. And what I know is that I see that there are markings here and here to show that these two angles are congruent. If this angle here, angle BAC, is in fact congruent to angle DAC, that means that this ray AC is an angle bisector. So it has sliced, in fact, this larger angle here into two equal parts. And that tells me a lot of information. One of the things it tells me, based on the angle bisector theorem, is that an angle that is a bisector creates an equidistance from here to here and here to here. In other words, if these angles that are formed by bisecting exactly in half create equal angles, it also creates an equal distance between that divider and the two ends that formed the bigger angle. Now, one thing we have to pay attention to with the angle bisector theorem is that we are talking about a distance and a measurement. So I am not going to talk about the congruence that I have here. I'm going to talk about the fact that segment BC is an equal distance or equal measurement to segment DC. And because those two things are equal, I'm going to do some substitution. That's what I would call it if I were doing a proof. And I am going to take out DC, replace it with 7.2, and I know that I have found the measurement of BC is 7.2 as well. So next we're going to look at this other diagram, and what I notice here is I have a right angle that is announced to me here as part of my given information, which probably means for this particular section I'm going to focus on the perpendicular bisectors, or at least I'm going to look at that as an option. I see that these two segments are congruent, and these two segments being congruent plus the right angle shows me that this is a perpendicular bisector. Now, what I know about a perpendicular bisector is that it creates a situation of an isosceles triangle where the point here on the bisector is equidistant from T as it is to V. So if I am looking for, again with my highlighter, I am looking for this segment here, I know that it's going to be equal in measurement to this segment here based on the information I'm given and based on the perpendicular bisector theorem. So in this case, we've got sort of a simple algebra problem we've got to solve. We already have all of the information again showing that we've got a right angle, so it's perpendicular, and we've got two congruent segments here showing it's a bisector. So we are going to then just set our two sides, our yellow side, which was 3x plus 9, equal to the side that I highlighted in pink or red, which was 7x minus 17. We quickly solve, and of course you would use, if you were going to do a proof, you would have to use your algebraic properties of equality, but we'll quickly subtract 3x from each side. We've got 9 equals 4x minus 17. I would add 17 to each side, so that 26 is equal to to 4x. If I take my calculator or do a little mental math, then I realize that my x is equal to 6.5. I'm running out of space. And in order to find the actual measurement of UT or TU, I would substitute that 6.5 in for x and solve. So in this particular problem, we are looking for the measurement of angle MKL. And I'm going to grab my highlighter again. We are looking for MKL. Okay. And the other information we have is about this other angle, JKM. We have an expression to describe that. We also see that we've got congruence markings on our segments here. Now, what we've got to pay attention to is we've got several factors that are really helping us out. The fact that these two segments have two things going on can lead us into the converse of the angle bisector theorem. Remember, if a ray bisects an existing angle, then a couple things are true. First of all, it obviously says that this portion created is congruent to this portion and also equal measurements. It also says that the distance from this outer ray to the bisector should be equidistant from, again, the existing ray, to this bisector. The way that they show that is with two symbols. So remember, we learned that the shortest distance from one point to another is the perpendicular distance, right? That right angle forms the shortest distance between these two rays. So the fact that we can see that the shortest distance between J and M is congruent to the shortest distance formed by this perpendicular line here, this right angle between L and M, if those two are congruent, now the converse of the angle bisector says that these two pieces are indeed, these two angles, JKM and LKM, are going to be equal measurements. So let's just talk about some of the pieces that would be typical givens in a proof that allowed us to use this converse of the angle bisector. First, over to the right, I'm going to write that I'm working with the converse of the angle bisector theorem. And the converse again says that if I've got two distances that are equal, then I know that I've got an angle bisector, and I can say that the two angles formed are also equal. So because these two are equidistant, then I know these two are equal. Some of the other information that I needed in order to prove this, right, was that, first of all, we had the congruence markings here. So these two, the congruence markings helped me see that I had the same distance from one to the other. But secondly, knowing that I had the right angles and that I was dealing with these two being the perpendicular lines, showing that I had the same distance, right? Showing that I had the shortest distance from one ray to the other also helped me use this. Now I'm allowed to say that the definition, by definition of angle bisector, I'm allowed to say that our angle marked in red, JKM, is equal to, oops, I forgot the M for measurement, excuse me. The measurement of angle JKM is equal to the measurement of our yellow labeled angle, measurement of LKM. Forgetting things as I'm writing. The measurement of angle LKM. And so what I would do if I were you then is just go through my algebra pieces and substitute. My red marked angle is 3A plus 20 degrees, and my yellow marked angle is 2A plus 26. Now solve for A, substitute back in one of those formulas, and you can find the measurement of actually MKL, but also in the process you'll find JKM. All right, so the last example we're going to look at is also going to rely on the converse of the angle bisector theorem. And I want to remind you and point out that there's two things that I notice. First thing I notice is that I've got two segments here that are marked congruent. Now, just because they're congruent doesn't mean that they're necessarily proving that I've got an angle bisector. What needs to be in place in addition to the congruence is that right angle, showing that this segment is the shortest distance from ray FH to ray FG. That's what and I've got another right angle here showing that this is the shortest distance. So I've got two distances, both of them with right angles, so both of them the shortest distance from one ray to the next, and they're marked congruent. So because those two pieces are congruent, those two distances, I can use the converse of the angle bisector theorem again as my way of establishing that I've got two congruent angles at the top. So remember, the original angle bisector theorem stated that if I had a congruent angle here and here, that I could say that these two segments were congruent. This is now the opposite. Now I'm saying the converse is saying if these two segments are congruent, then I can establish that the two angles are indeed are equal because they're being bisected by ray FH. Now to the question that we have to answer. We are asked to find the measurement of EFH, which I'll mark with yellow, EFH, given that EFG, which I'll mark in red, the bigger one here, EFG, is 50. So I know that my inkling is to talk about the two angles being added up and equaling 50. There's a faster way where we wouldn't have to use necessarily the angle addition theorem and things like that. What we could do is do what the book suggests and list our two measurements as a variation of what an angle bisector says. So what they suggest we do is we say that the measurement of angle EFH is equal to 1/2 the measurement of angle EFG. So the justification for that, if you needed it for a proof, would be definition of angle bisector. And by doing this, we actually have a really quick way to use substitution and then solve and figure out the measurement of EFH, which we kind of know is 25, but we also know if we're doing a proof, we have to put in all of the steps to show that. So we would then state that the measurement of angle EFH, is equal to 1/2 of 50. We'd substitute that 50 degrees that we knew from our given information. And then we'd be able to say that the measurement of angle EFH is equal to 25 degrees.